let's first define the concept of length. The meter, the SI unit of length, was initially defined as 1/10 millionth of the distance between the North Pole and the equator. Imagine that defining a human measure from the very shape of Earth itself. But as science advanced, we sought greater precision. Today, the meter is defined by something constant and universal. The distance light travels in a vacuum in one divided by 299,792,458 of a second. To put it in perspective, 1 meter is about 39.37 inches. For everyday scales, we use centimeters and millimeters. For longer distances, we use kilometers. Now mass. The kilogram, the SI unit of mass, tells us how much matter something contains. It was first defined as the mass of 1 liter of pure water. Later, it was represented by a physical artifact, a platinum iridium cylinder preserved in France. For over a century, this object served as the world standard. However, in 2019, it was redefined using a fundamental constant of nature, the Planck constant. A 1 kilogram object has the same mass everywhere, but its weight changes with gravity. On Earth, where gravity is about 9.8 meters per second squared, it weighs 9.8 newtons. On Mars, with weaker gravity of 3.7 meters per second squared, it weighs only 3.7 newtons. This clearly shows that mass stays constant, while weight depends on the planet's gravity. Next, temperature. Temperature is a fundamental physical quantity that represents the average kinetic energy of the particles in a substance. It provides a quantitative measure of how hot or cold an object is, and plays a central role in understanding thermal phenomena. Temperature determines the direction of heat transfer, which always occurs from hotter regions to colder ones until thermal equilibrium is reached. It is one of the basic parameters used to describe the state of matter and is essential in thermodynamics, chemistry, and physics. The SI unit of temperature is the Kelvin, though degrees Celsius and degrees Fahrenheit are also commonly used in everyday and laboratory contexts. Time governs everything, from atomic vibrations to planetary revolutions. The second, the SI unit of time, is now defined by the vibration frequency of cesium-133 atoms. This atomic precision allows scientists to measure time with extraordinary accuracy. Now that we have explored the fundamental quantities and their SI units, it is important to understand how these basic measurements can be combined to describe more complex physical properties. Many scientific quantities cannot be expressed using a single base unit. Instead, they are derived from combinations of 2 or more base quantities. These are known as derived units, and they allow scientists to measure and describe relationships such as volume and density. Derived units provide a powerful way to connect different aspects of physical phenomena through mathematical relationships rooted in the fundamental SI units. Volume is a derived physical quantity that measures the amount of three-dimensional space occupied by a substance or object. It is used to describe the capacity of containers, the size of solids, or the extent of fluids and gases. In the International System of Units, volume is derived from the base unit of length, since it represents length multiplied by width and height. Therefore, the SI unit of volume is the cubic meter. However, in laboratory and everyday contexts, smaller units such as the liter or milliliter are commonly used. Density is a derived physical quantity that measures the mass of a substance per unit volume. It describes how compact or concentrated matter is within a given space, and is fundamental in understanding the properties of solids, liquids, and gases. Mathematically, density is expressed as the ratio of mass to volume, providing a link between the amount of matter and the space it occupies. The SI unit of density is kilogram per cubic meter, although in many practical applications, grams per cubic centimeter are commonly used. Measurement and units are the foundation of scientific study, enabling accurate quantification, comparison, and communication of physical quantities.